Now in this video, I'm going to take a little bit of time to deconstruct this example we just did. So remember, we just did this example of the sort of simplest possible problem using Lagrangian. So just a ball falling under gravitational force. And for finding Lagrangian, we figured out what the relevant coordinates were, including both the position coordinates and the velocity coordinates. We wrote the Lagrangian in terms of those things, which was the kinetic energy minus the potential energy. And then we took some partial derivatives and eventually came up with the equation of motion. Well, let's take a minute to look at that for a second and think about how that connects to some of the ideas that we've already developed. So why does this make sense? And I want to argue that mostly from a sort of F equals ma perspective. I don't actually want to go into the principle of least action, which is certainly another and probably much more correct way of talking about why the Lagrangian approach makes sense. But I instead want to connect back to the ideas that connect potential energy to forces and think about how the Lagrangian actually plays out for these systems. So remember, the Lagrangian is written as the kinetic energy minus the potential energy. And when you get the equations of motion, what you're doing is you're taking the partial Lagrangian with respect to the position variables and setting that equal to the time derivative of the partial Lagrangian with respect to the corresponding derivative of position variable or sort of velocity variables. Okay. Let's think about that a little bit. In general, so usually, or at least for Cartesian, actually not usually, but for Cartesian coordinates, the potential simply depends on what the position is, right? And the kinetic energy depends on what the velocity is, right? So if you say that you've got some system where the kinetic energy is just a function of velocities, right, or of time derivatives of the variables, and the position is the potential energy is just a function of the position, then for that case, right, let's think about what the partial of the Lagrangian with respect to Q is. Well, the partial of the Lagrangian with respect to Q is the partial with respect to Q of the kinetic energy minus the potential energy. But the kinetic energy for the cases where the kinetic energy only depends on time derivatives of the position variables, the kinetic energy doesn't depend on position, right? So this thing, for those cases, actually is just a partial with respect to the position variable of the potential energy with a negative in front of it, right? And on the right-hand side, I've got d by dt of the partial of the Lagrangian with respect to q dot, but if only the kinetic energy depends on q dot, this is actually the partial of the kinetic energy with respect to q dot. And for Cartesian cases, so let's think about for Cartesian cases, the kinetic energy is always just going to be 1/2 m times x dot squared plus y dot squared plus z dot squared for a single particle. So this actually is going to look like things like m times, if I were taking a derivative with respect to x dot, m times d by dt of x dot, or m times x double dot, right? So the right-hand side here gives me mass times acceleration, right? And I'm actually going to get 3 different masses times acceleration. I'll get one when I take the partial with respect to x dot. I'll take one when I take the partial with respect to y dot, and one when I take the partial with respect to z dot. So this left-hand side looks like ma, right? And this right-hand side is the partial of the potential with respect to position. Well, if you remember when we talked about forces derived from potentials, when you take the derivative of the potential with respect to a position variable, you actually find out what the force is in that direction. So this left-hand side, for this case, corresponds to your forces, right? So in fact, in this sort of limited case, when you actually can write the potential purely in terms of the position variables and the kinetic energy purely in terms of the velocity of the derivatives of the position variables, the Lagrangian approach actually simply reduces to F equals ma. Now, there are plenty of cases where that isn't the case. So, for example, if you talk about a polar coordinate system, your kinetic energy does not just depend on r dot and theta dot, it also depends on r, right? And so then this analysis begins to fall apart, and it becomes a little bit more complex to see what the connection is between this and F equals ma. But certainly for this sort of limited set of cases, the Lagrangian approach really is just kind of a restatement of F equals ma. And I hope that at least helps you to believe why it is that this works, even though, in fact, there are lots of cases where it doesn't seem to sort of tie up quite as nicely, and really to understand it better, you need to talk about the principle of least action.